As was just mentioned, I am the MMIC design manager for Wolfspeed. We are a completely vertically integrated GaN-on-silicon carbide power and RF distributor and manufacturer. We do everything from materials growth to epitaxial deposition, device development, including the transistors, and then full MMIC design, fabrication, and packaging. So completely vertically integrated, and we have started moving as the technology's advanced and the needs have advanced up into the millimeter wave now. We've just released in the last year our 0.15 micron process to support that, and I don't think I could have gotten a better introduction than the whole, all the sessions in the morning, talking about exactly why these types of circuits are needed. So what am I going to be talking about today? Really three basic things. So why is there a need for GaN, and in particular GaN MMICs, in particular for millimeter wave applications? What makes a good GaN device for millimeter wave applications? There's a lot of things that go into it as you're designing the actual device itself. And then give a couple of examples of some recent millimeter wave MMICs that we've released. So why GaN? We talked about this a little bit earlier. We can make MMICs to address millimeter wave applications out of a lot of other things that are already out there and have a much longer history and track record. We saw a lot of talk about silicon and gallium arsenide and the spaces that they play in. So why is it that we want to use GaN? Well, the number one reason is power density, right? So a lot of these applications, particularly as you get more into the base station and larger power needs of some of these applications, GaN as a wide band gap semiconductor can provide much higher power densities due to the higher breakdown and the higher current capabilities. The next most important thing is thermal handling. So as we talked about earlier also, these are becoming much more, not only power hungry, but also getting much more compact as we move into millimeter wave. So the ability to dissipate and get rid of the heat that's dissipated in your application becomes more and more critical as you move up in frequency. This is also because as you move up in frequency, it becomes harder and harder to achieve higher efficiencies. If you're at a lower frequency, you can get much higher power out of a single die, say, because you're able to do power amplifiers that might have, say, 80% efficiency or more. So high power silicon is useful there. As you move higher and higher in frequency, you become more thermally limited just because of how much power you can dissipate and how much heat you can get out, and then also because of the reliability of the devices at those higher temperatures. So GaN intrinsically has a higher temperature threshold and can handle higher junction temperatures than a lot of the other technologies out there. So then you put those two together, and because of the wide band gap nature of gallium nitride, the high breakdown voltages, it allows us to approach higher bandwidth designs at the MMIC level. So as you get larger peripheries in order to make these higher power devices, it drives the output impedance of your device down. It makes it harder to match overall, and in particular harder to match over wide bandwidths. So again, down at lower frequencies where you're talking about, say, a base station bandwidth that's on the order of 100 megahertz, let's say, it's much easier to do that in LDMOS, where you can really peak up the design to get very good efficiencies over that. As you move higher frequencies, where we're starting to talk about needing gigahertz of bandwidth, or even more so if you move away from communications, let's say, and you're moving into an EW application or something where you need decades of bandwidth, being able to achieve sufficient efficiency in the amplifier so that you can get rid of the thermal issue becomes more and more critical. And being able to actually match those devices is easier when you have a wide band gap transistor that allows you to have a higher output impedance, because as you scale it up and you shrink down that output impedance, it's still high enough that you can match to it properly. And then last, of course, is what we call the king of the specs, efficiency. Doesn't matter how good of a part you make, if you can't make a good efficient design out of it, you're not going to be able to achieve any of these specs. And again, all those things that I've just talked about go into being able to achieve that type of efficiency, particularly over the bandwidths that are required in these systems. So why GaN for millimeter wave? We talked about this also. It's not necessary to have GaN for high power, right? I think Liam was talking about combining in a lot of these lower power things to achieve the needs that you need. But the downside is, as we're going into more complicated architectures, particularly for, say, phased array applications, we're going to become limited in the spacings that we have. So actually physically fitting these power amplifiers into the spacings that are required at millimeter wave becomes more of a challenge. So in order to do that, you not only need to be able to shrink the die, but you need to be able to shrink the die in a way that you can handle the thermal dissipation, that you can integrate the components onto a chip that is small enough that you can actually fit within the spacings of these systems. So having a smaller footprint, being able to mitigate the thermal concerns and improve the efficiency, all go into that same thing. So not only is the technical aspects of GaN sufficient for these types of higher frequency applications, moving to a MMIC will also help us with that. And as we talked about, to a great extent, the two biggest applications that are driving this right now are phased arrays, whether that's for radar or communications applications like 5G, and then also SATCOM, where it's not only size and weight, but also the power draw that's critical for these things. So again, now why do we want to use MMICs? It's not for cost. I mean, you can build most of these things more cheaply by going to a hybrid structure, but again, the problems with that is you're not going to be able to get performance over a wideband as easily. You're going to have assembly issues when you go to build these things at any kind of scale. You're going to have thermal issues when you try to space these things into a smaller area and push all these components down. So all those reasons that help us with performance at the GaN, because of GaN transistors, are just echoed by moving to a MMIC. So these things are going to allow us to go to higher frequencies with less concern about resonances and loss as we go to higher frequencies, push them into smaller spaces. A much simplified BOM, so from a standpoint of actually building these things and assembling them, the cost and the complexity of the build becomes much more achievable. And we're going to get more consistent performance. So again, with a phased array, if you're putting these things into an array, you need to make sure that they are matched or at least can be calibrated out across the entire array. Being able to build these and properly bin them such that they work out of the box in a way that's well matched significantly simplifies the assembly. So if we're going to make a high power, high frequency MMIC, what do we actually need out of the process, right? So first is high power density. So we want to be able to get a small chip size and better matching capability. As I said, the high output impedance of GaN relative to other applications or technologies such as GaAs or silicon allows us to go to much higher total peripheries and achieve even higher power density and total power in the same size and over a wider bandwidth. We want to get high Fmax and high FT so that we can actually achieve the PAE and minimize the drive requirements, right? This is how we actually get enough gain to get sufficient PAE out of the device to make it usable in an application. We want minimal intrinsic nonlinearity, so good AM to AM and AM to PM performance. Now, traditionally, gallium nitride has had, I won't say issues, but has had the characteristic of having a very soft compression. So in order to get peak PAE, you typically have to drive these things, 4 dB or so into compression for the output stage. We've taken that into account in our 0.15 micron process. So what we've seen is that we're actually able to achieve P1 dB efficiencies and powers that are within a half dB of our PSAT efficiencies through some engineering and some design in the bias circuitry. And I'm going to show a little bit about that on one of the MMICs that I'm going to discuss later. We need minimal dispersion, so trapping again is a native part of gallium nitride technologies, and that's really kind of intrinsic to how the high power density and the wide band gap is achieved. the epitaxy actually has to have some trapping in it due to the nature of the device. But there are things that can be done to mitigate that. And we've been working on that in order to get the minimal dispersion so that it doesn't have a negative effect on your efficiency and on your linearity. And then scalable geometry. So in order to make a good MMIC, you need to have devices and models for those devices that are scalable to the exact sizes and geometries that you need that are going to be applicable to the power requirements and frequency requirements for your application. And then last but not least, in order to really move into the highest frequency, having integrated slot vias in the devices allow you to minimize the source inductance, which is a key aspect to moving the knee frequency of the devices out and making them more applicable at higher frequencies without having to actually shrink the gate width and reduce your power. So I'm going to talk a little bit about all of these. So for device scalability, you can see here a few of the layouts that we've used and are achievable. So you can see that the devices are scalable in many ways. You can scale the spacing of the source to source and drain to drain pads across the manifold of the device. This allows you to make more compact devices. If you have lower frequency, if you have higher frequency needs and you need to minimize the parasitics, or you can actually spread these out if thermal is really what's driving the design. You can also have different size gates that are scalable for lower frequency versus higher frequency applications. You can also, if you need source to generation, or if you plan on using, say, a common gate configuration for a cascode device, you can actually use strapped sources instead of the slot vias. It does increase the source inductance, but in the case of a low noise amplifier, for instance, sometimes you actually want that, right? You want to use source to generation in order to help stabilize the device and pull the noise circles in closer to the gain circles. The key isn't necessarily being able to lay these out. The key is being able to model these and how these parasitics all actually get impacted when you do this. We've done a lot of work on our modeling side so that as we scale these devices with geometry, we're actually taking that into account and how the device is modeled for design purposes. So we get excellent correlation as you scale these, both in geometry and bias, to measure results. So there's a little bit of performance for our new G28 V5 HEMT process. This is the 0.15 micron process. And you can see that, depending on bias, you can easily get 20 dB of small signal gain through 50 gigahertz, and then down at lower frequency, upwards of 25, say at X band, 10 gigahertz. This is significantly better than what we were able to achieve on our quarter micron process, and is what really drives the ability to use this at millimeter wave. And you can also see that at 30 gigahertz on a 28 volt device, we're able to achieve 45% PAE and still have in excess of almost 8 to 9 dB of of power gain, associated gain. And then, as I mentioned, also reliability. So one of the key drivers and key aspects of gallium nitride is the ability to operate at higher junction temperatures. So we typically spec our junction temperature limits at 225 degrees C. And you can see for our V5 process, we've completed Arrhenius testing that projects out to 5e6 hours at a 225 degrees C junction temperature. And this was all done under RF alt. So this is actually RF driven temperatures with junction temperatures for the testing done at actual temperatures ranging from 360 to 400 degrees C in the junction. For this particular technology, the failure mechanism is a little different than our lower frequency technologies. Typically, we see cracking in the gate structure or the field plate structure in the lower frequencies. This is actually a different failure mechanism that has to do with metal mixing that occurs. The gate itself is actually much more robust. So we don't actually see catastrophic failure. When we fail these, what we typically see is a degradation in performance that's not recoverable. So we actually spec this as a degradation as opposed to an actual catastrophic failure. So this is an extremely robust process. So as I mentioned before, if you're looking at this from a design standpoint, one of the most important aspects is how good are my models, right? Model fidelity to what you actually measure is key to getting costs down and getting first pass success on a design. Not only that, but the model should work under a wide range of conditions. So you need something that is going to work at extremely high temperatures across a range of biases and frequency levels and drive levels. It should accurately predict the drive up curve, and you should be able to use it in environments that you may not necessarily be able to measure. So there's a lot of ways that you could actually model these things. We tend to use a compact model, which we can use because it's a self-contained model and it can be extrapolated. So a lot of the other device models that are prevalent out there, they are based on direct fitting of measured results, which is excellent if you have the specific device that you're interested in, and you know that you can actually measure to the range of environmental and use conditions that you're going to see. That's not always the case, particularly as a foundry. We don't actually know the application space that our customers are going to use, so we need something that can actually be used in any environment. Also, the model needs to be able to account for temperature effects. So as you dissipate more power in the device, obviously it's going to self-heat. The junction temperature is going to go up, and you're going to see the effects of that on both the capacitances and the intrinsic current of the device. That needs to be accounted for in the model so that as you drive these things, you are actually seeing the degradation that you're going to see due to thermal. And then access to the internal current source of the device is also a key component nowadays in design. This allows you to actually see what the waveform is at the current source of intrinsic to the device so that you can do the switch mode design that we were talking about earlier, and also so you can see the dynamic load line, which is very useful for things like distributed designs and understanding how you're actually loading the device. So here I've just got a few plots of the thermal self-heating aspects of the device model. So you can see in these top models, we've actually set the thermal resistance of the device to 0. So it perfectly conducts all the heat out of it. And you can see no matter what range of biases you apply to it and how much power you're actually dissipating, you don't actually see any rise in the junction temperature. It's at 75 degrees C across the way. While over here, you can see that there's no droop in the IV curve as we run these through the bias range. However, if we add some thermal resistance, such as you would actually see when you mount this thing into an application, run it at CW, you're going to see as you dissipate more and more power, the junction temperature is going to increase. So out here where we have very high currents and very high voltages and we're dissipating a lot of power, we're starting to hit that 225 degrees C junction temperature limit. And this is useful for two reasons. A, so you can understand the impact of that on your actual performance. And B, you want to know what that junction temperature is in order to make sure that you're within the reliability limits of our device. And then also you can actually see in the IV plane that you do start to see the droop effects of this as you increase the power. Now, as I also said, being able to actually model the proper RF performance of the device is also critical. So these are some load pull contours of various sizes devices and devices with different gate lengths, different frequencies. This is 10 gigahertz and 3.5 gigahertz. This was 10 gigahertz. I thought I had some 40 gigahertz data in here, but I guess not. And you can see that we have very good alignment of the RF contours for the model to measure for the optimal load. And that also, as we drive the device up in power, we're getting a very good model to measure correlation between the gain and the efficiency of the device as we drive it. And then similarly with both size and bias, we want to make sure that the S parameters are properly properly following the performance of the device. And we can see here from the Smith charts and the MSG charts that we are getting very good correlation over both a range of biases, where we're ranging it from 20 to 40 volts, and then from 10 to 250 milliamps per millimeter bias conditions, and over a range of device sizes at a given bias condition. And as I mentioned, this is just plots of the dynamic load line and the internal waveforms of the internal voltage and current at the current source of the device, which are necessary in order to do proper switch mode design and to understand how you're actually driving and loading the device. You can see whether you're current limited or voltage limited. This actually becomes extremely useful in the case of a multi-stage MMIC, where you need to understand not just what's going on the output, but also how you're loading the drive stages of that in order to drive the output, to make sure that you're not going to oversaturate that, and that you've got good bandwidth on bandwidth margin on your interstage matching. And then last but not least, I talked about earlier that there are effects within the GaN model, or the GaN device, I should say, due to the traps. And we have things such as current collapse and knee walkout that you can see when you do a pulsed IV compared to a DC IV curve. And those effects actually change depending on what your quiescent bias is. And if that's not properly modeled, then you can get inaccurate predictions of what your load line is going to be, which will put you into the wrong design space. So as you can see, we can scale the drain voltage anywhere from 15 volts out to 40 volts on our process, and we'll get very good alignment along the load line of those IV characteristics. So a few examples. This is a recent design that we've done at KA band. This is a 26.5 to 30.5 gigahertz MMIC. It's a 4-watt MMIC. We achieved better than 30% PAE over the band with 25 dB of gain. And as I mentioned before, it has excellent P1 dB. This is a 3-stage device. It's roughly 2 millimeters by 3 millimeters. But this was a first pass. There's probably some room for some size improvement here, but had some excellent results. So as I said, it was a 3-stage MMIC. It had a 1-to-2 drive ratio for all the stages, with 1.2 millimeters of periphery on the output, and it was run at 28 volts. The main things to take away from this is that there was a linearity improvement from both superior device performance plus some bias design that we did in this. The first stage was Class A, to keep it as linear as possible, and then the second and third stages were Class AB. And that lower bias provides for a little bit of gain expansion. So for what little bit of compression we did get, we were able to offset that. And then that allowed us to get both better AM to AM and P1 dB than you would typically see on a 3-stage MMIC. At a lower frequency with our other processes, a 3-stage MMIC, you would typically see the peak PAE occurring somewhere around 5 to 7 dB compression. So just some results. Small signal. As you can see, we had typical about 27 dB minimum gain through the band. This is actually a representation of one wafer's worth of devices, so you can see a typical spread there in the small signal. And then input and output match. Input match was off a little bit. That's certainly something we'll look at in the design. The bandwidth was correct, but we were seeing some peaking due to loss mismeasurement at up to about -7 dB. And then certainly good enough to S22, considering it's a power amplifier. Typically these things don't show perfect S22 because you're matching them for power, not for small signal. And the load does change, the optimal load, as you drive it up in power. So this is just a P in, P out measurement. You can see that at about 1 dB, 1 dB of compression, we're getting on the order of, 37 and a half dBm of power, and we're still at about 29 dB of gain in this case. This was for the center frequency at 28.5. So better than 5 watts at 1 dB compression. And then similar compression curves across the frequency band. You can see that we do tend to get a little bit of gain expansion, which would be negative compression. And then once we get up to about the 37 dBm power level, we're at about 1 dB compression. A little actually better up at the mid band. And these are just plots of the output power and the PAE taken across frequency at P1 dB, which is the blue trace, and PSAT. And you can see that there's really only about a half dB of separation. So very atypical for a MMIC amplifier to have the P1 dB power this close to the PSAT power. And we're able to achieve in excess of 30% efficiency across the frequency band under both conditions. And of course, why would you want better AM to AM? It's in order to get better linearity overall. And we can see here that at 34 dBm, which is 3 dB back off from PSAT, we're achieving better than 20 dBc of isolation. And if you go to 6 dB back off, we're down to minus 30. So typically, something like minus 15 to minus 17 at 3 dB back off or 4 dB back off would be, for a non-corrected device, would be very good. And in this case, we're seeing 3 to 4 dB better than that. So another application, this is a KU band wideband Doherty MMIC. So typically, Doherty is used more often down at lower frequencies, and it's typically used in hybrid configurations, simply because the complexity of the circuit and the sensitivity of the circuit is very high. So putting it into a MMIC, you really need to have excellent models and an excellent understanding of the design in order to make sure that you're going to actually see the Doherty action in there, because once it's designed, there's no tuning it. Also, one of the advantages of doing a MMIC is this is actually a 3-stage Doherty with all 3 stages, in both the peaker and the carrier amplifiers within the Doherty. So the input splitter is before the first stage, and the output. We actually did multiple versions of this with different numbers of stages within the Doherty, and it's basically a trade-off of efficiency and linearity versus achievable bandwidth and sensitivity. So this form actually gives you the best efficiency and better linearity. If you really need very wide bandwidth and low sensitivity for, say, manufacturability, you could do the first 2 stages as a driver, and then the output stage would be a Doherty. But in any case, with this design, we were able to achieve I should mention that it is an asymmetric Doherty, so you can see that we've got a 2-to-1 ratio for our peaker and carrier amplifiers, and that's to achieve a 9 dB peak to average ratio in the design. This was a 17.2, it was actually a 17.2 to 20.2 design. There's a little bit of roll off, but over the 2.5 gigahertz of bandwidth up here, we did get 13.5% bandwidth, which is much higher than you typically expect to get out of a Doherty. That is one of the key trade-offs, is efficiency versus getting the Doherty action for efficiency versus bandwidth. And this does have different bias conditions, because you need to bias both the peaker and the main carrier amplifier at different conditions. One's Class C, one's more of a Class AB. So some results again. Over 30 dB of gain across the band, minus 10 dB input and output match, which is excellent. And here you can see the classical Doherty action. So peak saturation up here around just under 2 watts, and then at 9 dB back off down here at 27 dBm, you can see that we're still getting excellent efficiency and getting better than 25% over all, except, as I mentioned, that 20.2 gigahertz range, and over a slightly smaller 1.5 gigahertz range, which is still 10%, we're seeing better than 30% efficiency. So excellent results for a Doherty in general, considering the bandwidth, but particularly considering that it's at about 3 times the normal frequency use of these things, and it's in a MMIC form, really exceptional. And then again, we can see the back off and full saturation peak operation. P out of, again, a little better than 32 dBm, and then 27 dBm for the back off, and you can see that we're maintaining that efficiency across the band. So that's it. GaN on silicon carbide. The MMICs can provide specific advantages for high frequency, high power applications, smaller size to make it actually integrable into some of these phased array applications, and better handle thermal because of in these densely packed systems, because of the higher thermal conductivity of the silicon carbide substrate, and also the higher temperature junction temperature robustness of GaN intrinsically. And then you can reduce design sensitivity compared to chip and wire or pre-assembled devices, which is the main reason that in particular the Doherty amplifier was pursued in this application at these frequencies. And
thank you very much, Jeremy.